So I'm going to talk about some data structure tips and tricks. My name is Darren Ohashi. As Kashka said, I'm a senior architect of Maplesoft. So for this talk, I'm going to be working through an example that I think that it's a simple example, but it's helpful for what we're going to be talking about. I'm going to read and analyze words from a text file. So this is an interesting example because we don't really know anything about the input, right? We don't know what words are going to appear. We don't know how many words there are going to be. There could be one word, there could be a million words. Um, so we have to be flexible. And these unknowns are going to mean that we're going to want dynamic data structures. So I'm mostly going to be talking today about arrays and tables. And when I talk about arrays, I'm only going to be talking about 1D arrays that are indexed starting at 1. So in Maple, you can create multidimensional arrays and you can have custom indexes. I'm just using basic standard arrays and tables. So our first very simple example, we're just going to read all of the words from a text file. So this is just a basic do loop that will break when the file is read. We're going to start by storing the words in a dynamic array. So we'll create an empty array using the array constructor and passing the empty list. And then we're going to use array tools append to add elements to the end of the array. So, like I said, this is very simple, but you know what? This is a really good way to, if you don't know how much data you're going to get, to start off by reading your data in. So we've got all of our data read into A. So we ask how many words are in A. We can use num_elements A. What's the first word? Well, just A of 1. The first 10 words, you can use a range for the index, and Maple will return you those 10 elements. You can use negative indexing, so you can start at the end of the array to get the last element. And similarly, we can get the last 10 elements using a range. So now we can ask a more complicated question. Was a particular word in the document? So how will we do that? So here's one way. You can use a for loop. We'll basically check every word in the array, ask, is this the word I'm looking for? And if it is, we'll stop. The problem is this is really slow. You have to look at the entire array, every element in the array. So question is, can we do better than this? And you shouldn't do this. You should just use member, which is a built-in function. But this is how member works. And it's going to be order n, even if you use the built-in function. So let's talk about a few other array operations while we're here. So arrays work with all the basic Maple functions that you're probably familiar with. Map, seek, add, sort, all those good things. We also have an array tools package. And the array tools package has some basic commands like extend, which allows you to append multiple elements at once. Insert, which lets you insert into the interior of the array. And remove, that lets you remove elements from the array. And higher level algorithms like partitioning, reversing, and that sort of thing. Now, if we're going to talk about array performance, there's some interesting things to think about. So appending and extending and removing from the end of the array will be on average time proportional to the number of elements you add or remove. So this is mostly going to be constant time. But if you insert or remove from the middle of the array, that's going to require moving all of the elements after the position of your change. So it's best to think of that as being like an order n type operation. So if you're working with an array and you want your best performance, you want to add and remove elements from the back of the array. Sometimes this can be a little bit opposite from what is natural. But like I said, array tools has a reverse function, so you can do your work and reverse it back into the order you want it. That's great. The other nice thing about arrays is since they can be modified, we have a bunch of functions that work in place. So if you don't need the original data working in place, you can save that memory of having to allocate a new structure. So as an example, map in place, f of a, will apply f to every element of a and then write that into the original array. So this is what might be called a transform operation. You can sort in place. Here's a fun one that I actually recently discovered. So map has some fold reduce type operation functionality as well, but you can do reduce equals null. And that tells map that you're not interested in the return value at all. So you can call a function like printing or something over every element of your array. This works for lists and things as well. And it won't construct a return value. And if you don't need the return value, that can again save you some time in memory. In Maple, saving memory is often saving time. All right, so let's say we did care about what words, the actual unique words that were in the file. So we're going to do this again now, but we're going to load into a table. So in other programming languages, a table is often referred to as like a dictionary or a map. It's a key value pair. So you give a key and you can store a value, and then if you give that key again, you can get that value out. One interesting thing with Maple is that basically anything in any expression can be a key or a value. And that makes for some interesting possibilities. The other nice thing is that we have constant time operations for insertion, deletion, and asking is something in the table or not. So for example, in this case, if we just start filling up the table using the words that we find as the key and just using null as the value, because we don't really care about the value, well, we have basically a dynamic set where you can insert elements, you can remove elements, and you can ask, is this word in the table in constant time? So how many unique words will we find? Well, again, we can just use num_elem of t for that. How do we get a list of the unique words? Well, we can use the indices function, which is a function that works with tables to return the list of all the keys. We can ask was word in the document by just asking is t of word assigned? And this is going to be constant time. And then we can remove something from t by unassigning t of word. And again, constant time. So let's take it a step further. Let's say now I'm interested in the word frequency. How many times do the words appear? So we're going to use a table again, but now we're actually going to use the value for something. So we're going to use assigned t of word to see if we've seen the word already. And if we have seen it, we're going to increment the counter, which is the value. Otherwise, the first time we just set it to 1. All right, so how many times did word appear? Well, the value of t word. What was the most frequent word? Well, this is a little bit more interesting. I'm going to use a for in loop over a table, which is actually something that works, but it has a little trick to it because tables in Maple have what we call last name evaluation. So you actually need to wrap the name of the table in an eval for this to work. You actually have to have the table and not the name of the table as the if clause here. But for this loop, you then get all the keys and values of every element in the table so that you can look for the maximum. They're the element with the maximum number of appearances. The other reason that this is nice is we can do this without having to create a list of all the names or the keys, right? Which could, for a very large table, be a really big list. Now, if you do want to do that, we can call indices with the pairs option, and that will return the keys and values as pairs as equations. So let's say you wanted to sort all of the words by their frequency. So we could use a sort command here like this. And in this case, I'm going to use the key option. Now the key option to sort does a nice thing where it applies a function to every element of the input, and then it uses the return value of that function for sorting. Now the reason this is useful is because you only apply the key function once per every element in the input. Whereas if you give a comparison function, it'll actually get called n log n time. So sometimes that can actually make a difference in your performance. Now, on the flip side, let's say you have a really big table and you're worried about space. So we can do some tricks here to have a smaller output, or to use less memory, I guess I'll say. So first off, we can tell indices that we want our output as an array. And then when we sort, in this case, we're going to use just the comparison function. Right-hand side is quick enough that I'm not overly worried about the performance of having to use the key. And we're going to tell sort that we want to sort in place. In the previous example, that list that we created from indices is just thrown away. In this case, we can work in place and put our sorted list right into that array. And this can actually save quite a lot of space if you've got a large table. All right, one more. Now we're going to collect even more data. So now, along with the count, let's collect the index for every index for every instance of the word. So we'll go back to our loop. We're going to add an index variable for the for loop. So that's just going to keep track of how many words we've read in so far. Now we're going to use a record to store the name data. So we're going to have two fields in the record, one for the count, one for the index. We're going to use an array in the record to store the indices. So for the first time we see the word, we'll set the count to 1 and the index to just I. And then every time we re-encounter that word, we'll increment the count and we'll append another word to the index. So now we can ask, how many times did word appear? Well, now it's word count. What's the first appearance of word? Well, now we have that list, so we can just look in the index. Now we're going to ask one more interesting question. What's the first word? If we think about the way we have our data structured, we actually don't have a very good way to find the first word. So here's one option. It's not great, right? So we do another for in loop over t. We look in the index for the number 1, which will be the first value, and when we find it, we stop. That'll work, but it's not great. And do you remember when we were using an array to get the first word? We just said A1. That was it, constant time. This is order n on the table. And this comes down to sort of what my final point was going to be. How do we pick the right data structure? You got to think, first off, how much data are you actually going to work with? If you know your n is small, O of n can still be really fast, right? So if you know you're working with a small amount of data, you're okay to even use an array if you have to scan through it linearly. And in fact, that can often be faster because although constant time operation, tables and arrays both have constant time operations, the constants on arrays are small, the constants on the tables are larger. So if you know that n is small, you can get away with doing linear scans. Now, the warning here is you have to know that n is small. It happens fairly frequently that you'll write some code and be like, well, no human being's going to enter more than 100 arguments. And then someone writes a piece of software that outputs a maple file. Now you have 1,000,000 elements from a computer-generated input, and your small input doesn't work so well anymore. Or your algorithm doesn't work so well anymore because you made an assumption over the input size. The next questions you should consider are your access patterns. So what is it that you need to know about the data, and how are you going to access the data? This is actually quite important. So for example, if you actually care about the order of the words, maybe you want to use an array because you want the first word and the second word and the third word. But if you care more about how many times does a particular word appear, a table will let you access that very quickly. And of course, unless you're really worried about memory, you can use both, right? And by combining both, you can get the best of both worlds in sometimes. So for example, if I ask the question, how many times does the 7th word appear? You might, if you just had an array or a table, either of those is going to be order n time. If you've got both of those, you can do it in constant time, right? You can look up the 7th word in the array and then look up that word in the table, and both of those operations are going to be constant time. So,
Minutes.
okay. Yeah, unless you're really concerned about memory, and these days memory is often less of a concern than it used to be, it's okay to have more than one data structure and to cross-reference between those data structures. Use what each of them does well. And that's the end of my talk. If anyone had any questions, I'm more than happy to answer.